Welcome back. Okay, so let's solve different questions also when the range of theta is discrete case, or when the range of a random variable depends on parameters that we cannot use differentiation method, and invariance property of MLE also a good property. And for nonlinear equations, how we get them MLEs. So we will discuss these. We will discuss the advantages and disadvantages of MLEs, and we will finish this estimation section and start talking about the properties of estimators. Okay, so let's continue with another example. So here in this example, we assume that we have only one observation. Okay, not a random sample of size, and just one observation. Okay, is taken on x also discrete random variable x with PMF f of x theta, where the range of theta is given as 1, 2, and 3. Okay, so find the MLE of theta. Okay, so PMF is given like that. So x can take 5 values, 1, 2, 3, 4, and 5. And theta takes values 1, 2, and 3. So this table is given to us also. So the probability of getting 0 when theta is 1 is 1 over 3. Same for 2 is 1 over 4, and 0, 1 over 3, 1 over 3, 1 over 4, and 0, 0, 1 over 4, 1 over 4, 1 over, okay, so 1 over 6, 1 over 4, 1 over 2, and last one. Oh, we don't have, I skip 2. Okay, I forgot counting. Okay, so we have 2, 3, and 4, 0, 1 over 4. So based on this information, we want to find the MLE of theta. So how can you do that? Think a little bit. Okay, so what's our aim? So we want to find the value of theta which maximizes the likelihood function. Likelihood function for a given value of x. So this part is important for a given information. So for a given value of sample observations, here x. Okay, so we know the possible values that x can take. Okay, so these 5 values, and we know that for which theta value this for a given x the probability is maximum. So these probabilities basically of each likelihood function. So likelihood function values actually. So when theta is 1, the likelihood values of 1 over 3, 1 over 3, 0, 1 over 6, 1 over 6. When theta is 2, the plausibility of obtaining 1 over theta as 2 as 1 over 4, and for last one is 0. Okay, so these are basically the plausibility or likelihood of obtaining these several parameter values like 1, 2, 3 for a given sample. So here, what is likelihood function? So let's write the what is our likelihood function here? So we have just one observation. It's same as the mathematically the marginal distribution. So here we have to think about, so basically our likelihood function is this one. So we want to find for which given x value this likelihood function maximized. So we have to look at the function this way, okay, and this way, and this way, and this way. So these are the observed values of sample. For x equals to 0, for which value of theta probability is maximum, the likelihood is maximum. We have to check that. So for which value it's maximum? So here for 1 over 3 it's maximum. For when x equals to 1, if we observe x equals to 1, then theta should be 1. So this will be the MLE value. When x equals to 2, we have two options actually, 1 over 4 and 1 over 4. Theta can be 2 or 3. When x is observed as 3, then the likelihood is maximized when theta equals 3. Okay, and when we observe x equals to 4, then again when theta equals to 3, the likelihood is maximized. Okay, so then let's write the maximum likelihood estimators for different observed sample values. So when x equals observed as 0, the possible value for theta, so we want to find a possible value of theta based on the sample information. Then since theta equals to 1, this probability, the likelihood maximized, so the possible value of theta hat will be 1. When x observed as 1, again the maximum likelihood obtained for theta equals to 1, then the maximum likelihood estimated when x is 1 is 1. Okay, so when x obtained as 2, then the maximum value of the theta can be 2 or 3. And if you observe 3 as our sample point, then the likelihood function maximized when theta equals to 3. Okay, and similarly when we obtain 4, the likelihood function maximized again at 3. So this is the MLE. For different sample points, we observed different values. Okay, so at the beginning we don't know, but if we take a sample and if it appears as 3, for example, we can say, okay, if I observe 3, then the maximum likelihood estimated for theta should be 3. I have to work with like that. Okay. Now, if we cannot use differentiation methods to find the maximum likelihood estimator case, so basically you have to use some logic to find the estimator using the definition of the maximization basically. So let's say we have a random variable from uniform 0 theta. And if you remember the PDF form of uniform, it's 1 over theta, where the range of theta is from 0 to theta. Okay, so for this concept, basically there should be an equality sign, although it's discrete, although it's continuous. Equality, probability of equality is 0. In MLE calculations, you have to use this equality sign to find the estimators, MLEs. Here, let's assume that we have a random sample of size n again, and our parameter space is theta, such that theta positive actually. Okay, so let's write the likelihood function. Okay, so when we write the likelihood function, we are multiplying our PDF for different xi values, multiplication of marginal PDF. So we have 1 over theta to the n. We don't have any x term here actually, and we need to write a range for theta. Okay, so actually we don't have any x value, but let's see, take the log likelihood function minus ln and take the derivative. You will see basically we don't have any solution here. Minus n over theta, so it's not 0 basically. We cannot find the local maximum. So no local maximum in the parameter space. Okay, so then, but we know that our likelihood function has to be maximized somewhere. Okay, so when we draw the likelihood function, try to draw the likelihood function, the shape of the likelihood function, and then see what shape we have, and then we can try to guess which value of theta gives us maximum likelihood. Okay, so our likelihood function is 1 over theta to the n. Okay, so when we draw the shape of the likelihood function, when theta increases it should get decreased. So we have such a shape here. Okay, and basically for some values of theta, it's 0 basically when theta close to 0. So we will see that this part goes to infinity. Okay, so it converges to infinity, goes till infinity. So we need to find actually at here. So which xi value maximize it. Okay, so here each xi value appears here. Theta is the maximum point for the xi values, you know. So we have each xi value in this region. So our question is, which value maximizes the likelihood function? Likelihood function for a given sample. I yazmadım. Okay. So okay, so we have to consider now, let's look at the form of the likelihood function. Okay, so it is 1 over theta to the n. So this means that, okay, so L theta is 1 over theta to the n. So which values of theta maximize the likelihood function? Basically, the minimum value of the theta maximizes the likelihood function, right? So this likelihood function is minimum when theta is minimum. Okay, so we are trying to find the maximum value, so we have to find the minimum value of theta. So how can we do that? We cannot differentiation, then we have to look at the range of boundary of theta and then try to see which value of theta minimizes the likelihood function. Okay, so this is the range for x, or the range of theta in terms of likelihood function basically. So let's focus on this one. So we have each xi value should be less than or equal to theta. Let's put an equal sign also here, it doesn't be important. So we have a sample of size n. So this means that each xi value, okay, so x1 to xn should be in this range. Okay, so if we order them, then this means that the minimum value should be greater than 0, and then the second bigger value, and goes like that, and the maximum value like that. Okay, so we are trying to find the lower bound for theta based on sample information. Okay, so here when we focus on the range, so what is the minimum value of theta? What is the minimum value of theta? Is this one. Okay, so we have lower boundary as the maximum value of theta. Okay, so the lower bound of theta is xn, maximum of each xi value. So this means that minimum theta equals to xn. Okay, so we know that minimum theta maximizes the likelihood function. Okay, so we found the minimum value of theta. So this should be the likelihood function because it maximizes the likelihood function. So this means that theta hat should be the maximum order statistic. Okay, so the possible minimum value of theta maximizes the likelihood function. Maximizes the likelihood function. So it gives us the MLE. Okay, so basically we will use this approach to be able to define the maximum value of the likelihood function. So let's consider another example here. So let's say again we have a uniform distributed random variable, but here right now let's say uniform theta to 1. Okay, and again let's say we have a random sample of size n. So let's define, the question is find the MLE of theta. Okay, So let's find the likelihood function. So it is 1 over 1 minus theta to the n, and theta xi1 is the range for theta. Okay, as you can see, again, in the form of the likelihood function, we don't have any x term, and we cannot find the maximum value of the likelihood function by differentiation. So cannot find maximum point by differentiation. Again, we need to use inspection. Okay, so which value of theta maximizes the likelihood function? So you have to ask such a question. So which value of theta maximizes the likelihood function for a given sample? So basically with the MLE we need to answer this question. So when we look at the form of the likelihood function, so you will see that so we have a negative sign here, it's in the denominator. So when theta increases, basically our likelihood function will increase. Okay, so our theta maximizes for the maximum value of theta. So we need to define maximum likelihood of theta, maximum value of theta based on this given range. So theta is less than or equal to 1 then. Okay, so this means that each xi value is bigger than theta. So when we ordered them, so we can get more precise range for the theta value. Okay, xn and 1. Okay, so what is the now exact closed range for theta? Is this one. So basically the range of x2 is x1 and x3 here. And range of xn is xn minus 1 to 1. So what is the range of theta? It should based on the minimum x1. So maximum theta obtained by maximum value of theta. And what is the maximum value of theta? So we are putting equality sign because of that one. If we don't have equality sign, we don't have the MLE in this case. We don't always have MLEs. So the MLE should be the smallest order statistic. Okay, so first order stat. Okay. Okay, so after I think you understand how to find the maximum points if we cannot use differentiation, how we can find the maximum likelihood estimate. Okay, so we have a good property of MLEs again. So we have an invariance property, like the method of moment estimators. If we found MLE of theta, if this is the MLE of theta, and if g theta is a function of theta, then the MLE of g theta is g theta hat. Whatever the function is, it can be nonlinear function, linear function. For example, for the previous example considered, let's try to find the MLE of 1 over theta cube. Okay, so what we have to do, just replace theta by cap, the MLE. And what is the MLE? x1. Take the third power. Okay. Or another example can be, let's say we have an exponentially distributed random variable. We already found the MLE as x bar, if you remember. Okay, so MLE was x bar. We already checked that. Let's find the MLE of probability that x less than or equal to 2. Okay, so what is probability that x less than or equal to 2? So this is the cumulative distribution function at point 2. So for exponential, it is 1 minus e to the minus 2 over theta. So when we consider the MLE of probability that x less than or equal to theta, only thing that we have to do is replace this theta by theta hat. Okay, so it is 1 minus e to the minus 2 over x bar. If you want to find the MLE of other functions of theta, or a function of some x, so all we have to do using invariance property by the invariance property. Okay, so we can ask also, let's say, find the MLE of the median. So you have to know how to find the median, right? Remember, first find the median. What we have to find the median? We need to define if m is the median. It should be 0.05, and we need to solve for m. Okay, so 1 minus e to the minus m over theta equated to 0.5. Then we will get e to the minus m over theta equals 0.5. Okay, then take the ln 0.5. So m equals to minus theta ln of 5. Basically, this is positive because ln 0.5 is negative. With this negative, it becomes positive value. So we want to find the MLE, then use the invariance property to find the MLE of m. Okay, so MLE of m equals to, so what is our form? Minus theta ln of 5. So put a cap here. What was theta hat is x bar minus x bar ln of 5 will be the maximum likelihood estimator of the median. Okay, so you can find the MLE for the quartile, first quartile, second quartile, third quartile. This is the second quartile. Also interquartile range or any other functions, you can find it. Okay.